how's it going with EMS, at least? Is there anything you guys want to speak about before I start explaining kind of this week's work? Is it like any specific things?
Nothing really, except I'm trying to get a link for this meeting so we can send it onto the WhatsApp group, because I think other people want to join, but they can't access or can't log in or something.
Oh, really? I did make an announcement. I don't know if it came through. There's like that join. Let me see. I'll try to do it myself. Maybe I didn't do it right because I did it on my iPad. Let me see. Can't reach this page. Okay. There's a problem. Let me go here. Let me just figure this out. Meeting options. I see, that's why no one was joining. Let me go here. Someone always manages to get a link. Right here, maybe. No? Show participants. Share invite, here we go. Copy meeting link. Let's go. So I'm guessing you guys have teams and you're on the teams and you joined it that way.
That's how I joined for sure.
Okay, cool. I must just remember maybe to trim this recording. And no, please don't say my network's now giving problems. Oh, there I see everyone saying. Let me make a new one. Okay. Sent a new link. There we go. Okay, cool. We'll wait a little bit. Is there any, maybe let's start with the quiz. Now that all the marking's done and everything's been kind of posted about that, is there anything concerning that maybe we can speak about? If we'll let anyone wants to speak about anything regarding that. There was just the bit of contention around that 0 marks for the magnitude. That I think lots of people confuse that, but I don't know if anyone needs that to be explained now. or if they're all fine, or if there's just anything, maybe we just wait before we start this week's work. Just wait and listen. Yeah. Let's just wait a little bit more just to see if more people come. But yeah, it sounds like people are going to be taking a break. Because it's also, if it's recorded, it's completely understandable. You guys being diligent to be here so that you get it done and out of the way and don't have to watch the video later, or there are questions that you want to ask. Oh, look, okay, good. More people are joining. Also, is my connection fine? Because I know it's like about to rain, it looks, and my Wi-Fi is a bit bad, especially when it rains. So we'll see now when I share my screen if that's fine. That's going to be the real test. Okay, I'm going to start. Let me share my screen. Guess still waiting to join, we can admit. Not video. Okay. Cool. If there's any, I'm just going to continue to this week's work. If there's any sort of questions, just type them in the chat. I have it open on my laptop here so I can see those questions. So yeah, let's start with this week's work. It's on magnetic coupling. I don't know if you guys have at all looked at that. It seems like it's a hectic time, but I think that's what I'm going to use this tutorial to go over, just to give a bit of understanding around that and sort of my take on it. So you have sort of two resources, and also to address quiz things. Get that thing finally out of the way and done. So yeah, that's kind of the plan today. So yeah, just type those questions there. So we're dealing with magnetic coupling. Magnetically coupled things, I think is what I labeled it there. And what exactly is magnetic coupling? Hello? Are you going to say what magnetic coupling is? No? Going to mute. Okay, so magnetic coupling is what happens between objects. Okay, so an inductor with the loops between the wires, we have these magnetic fields between the wires. You have interaction over a distance with magnetic fields. So we'll have like a wire and it will have a current. And if something has a current, we'll know it will also have a magnetic field. And then that magnetic field that it makes will interact with other conductors, for example. So if you have another conductor and it's in the presence of a magnetic field, it will cause a current. Maybe that current will make a magnetic field, and then it can interact with all kinds of things. So they can link with each other. That's the coupling part. The things are coupled together. So I think it would be good to just overview some basic laws. Okay, well, they're not basic, but they're kind of the basis of our electromagnetics. I think it's quite useful to have a description of those. So if we have this, okay, the closed integral of magnetic field with respect to length, which is equal to mu naught I. You guys might have seen this. This is saying that the closed integral, so if you have some path and it must end up where it started. If you take the dot product, so remember we're dealing with a vector field. So a vector field just means that at each point in space, so if we have x, y, it can be z as well. Well, it is z as well. I think you actually have to have z. Each point in space will now, how it could normally be a value, so we could say that this point is 5. Instead, that would be like a scalar field. But now we're dealing with vector fields. So a magnetic field is a vector field. So at that point, instead of saying that there's a value of 5 or 10 or -3, we say that there's a vector. Okay, now the vector will have some magnitude and it will have a direction. Okay, and this will be an XYZ, it can be an XY, it depends on what kind of analysis you're doing. But typically this is XYZ, 3 dimensions for these fields. So we have this field and we're seeing how aligned is this field with a path. Okay, so we have a vector field of B. So normally they'll put like a little arrow on top of it. And they say how aligned is it with this path. So if we have a vector field like this, for example, we could do the dot product of all of these vectors. So at each point in space, there'll be a vector, a direction, and a magnitude. And you'd say, how aligned is it with this path? And you have to define the direction of this path. And we'll say, okay, over here, it seems very aligned. So the dot product will give like a high answer. It'll be like some factor of how aligned it is times by its magnitude. And then over here, it'll be very aligned. Over here, you see it's perpendicular. It's not aligned at all. So that could be like 0. And basically, we'll add all of those up. So that's the integral part. We add them all up. And then when we add all of them up, we get current. That's what this is saying. So it's saying, just to draw it more simply now, it's saying that if we have a magnetic field, okay, and we draw whatever path we want, and we say how aligned is that magnetic field to this path, the amount that it is aligned to it, so going in the same direction that we define our path, that will tell us the amount of current trapped inside it. That will tell us the current inside it. So you can look at it in the reverse way. If we have a current of a certain magnitude, we times that by permeability. This is our constant that's relating between current and magnetic field. This is kind of in the medium that you're in will determine this. So that's why it's a material property, permeability. If we start with the current, we can say that we can draw any shape. And if we were to do the dot product and say how aligned the magnetic field is, so we could draw an arbitrary sort of shape, whatever we want, as long as it's a closed path like this, let's say. Okay, and if we were to say at each point on this path, and we'll say, okay, well, the path is going in like a counterclockwise sort of direction. I think that's counterclockwise. And if we take the magnetic field and we say how aligned is it as each of these points by doing the dot product, that's the same as the current, but it will also that it will be like it's coupled. The intensity of how aligned it is. So yeah, it's a bit confusing. You have to kind of play around with this to understand it. If we look at a conductor, okay, so I'm just building up this from basic principles so that you'll know when we eventually arrive at the formula, you'll be there. You'll see what's happening. But I think it's nice that we see the basic principles. If we have a conductor like this, and it's carrying a current, and we'll call that current. Okay, it's carrying a current, and we'll call that current I, capital I, variable I. Because this is kind of a symmetrical thing, we can kind of say, how will the magnetic field look around this? If we have a current, I want an answer from someone here, if anyone's listening, but I want to know kind of what do you think in a cylindrical conductor, what shape do you think the magnetic field, like what is the magnetic field doing around a conductor with a current flowing, a constant current? Who knows? Someone must have an idea.
Is the magnetic field not wrapping around the conductor in a circular manner?
Yes, exactly. It's going around this field, this conductor, in a circular manner, and the direction that we say is positive is the right-hand rule. Okay, so that right-hand rule is literally, it comes from maths. It's not even physics. It comes from maths that we define directions to be positive. So like if you define the x and y to be positive like that, we also define rotation to be positive. So yes, if current is flowing to the right like this, if we wrap our fingers around it, so if you have a pen in front of you, hold it in front of you and look at that pen, hold it with your right hand, and you'll see your thumbs pointing in the right direction if you're looking at it with your wrist up. The current's going in that direction, and then the magnetic field is wrapping around that, wrapping around the pen. Okay, so yes, it makes circles, and it circulates around it like this, and it will go all around it, kind of, and expand out around it. Now we can ask ourselves, what is the strength of the magnetic field? Okay, so what is, if we define, let's just define some axes. Okay, we'll define this as x, the distance away. So if we have the cylinder going whatever direction that is, we could call that z, whatever, it doesn't matter. We're just saying the distance away from the center of the cylinder, so that it's perpendicular like this. We're going to call that x. Okay. So we can say that we'll set our path, our closed path. Okay, we're going to set that to a circle. Okay, and we're going to set it a circle in the way that we predict the magnetic field's going to be. Okay, we're just doing this so that our analysis is nice and simple and we can actually do it by hand very easily. So we're going to say that it's a circle that its radius increases along x. So it's in the field of this. So we'll say that our circle, our path, is equal to a circle of x, okay? And then if we actually do the path integral of that, so that's when you add it all together, we're going to say, okay, wait, let me just write what I'm working out. So we're working out this, the closed integral of magnetic field times by, the dot product with the direction of that path. So then that will become, if it is completely aligned, it will be whatever the magnetic field is, the magnetic field intensity at that point. Okay, we'll say that it's going to be a function of x for now. And we'll say that because it's completely aligned, it will just be the circumference of that circle. It will be 2 pi x. So depending on where you're looking, it will say it's 2 pi x because it's completely aligned. So if I draw my circle, okay, this is the path we're dealing with. There's where so we're looking at it like kind of head on here. Here's our conductor. Here's x. Okay, we're saying that our magnetic field, okay, I've drawn actually this arrow the wrong way. No, I think it is, this is counter, which one's counterclockwise? This way. No, oh my goodness, imagine that. Whatever. Okay, so this is aligned, completely aligned with it, because we're saying it. So then we'll know that the dot product will actually just give you that length. Now, okay, but please, don't no one be scared about what's happening right now with all these crazy path integrals. You're not expected to do path integrals in this subject. Well, for this section, I don't know, maybe for the other ones you might have to do, but I don't think so. This is just kind of the derivation, so you understand when you see something like this in Maxwell's laws, what's going on. What does it actually mean? I'm just kind of deriving it in a simple way because I think that's valuable. So anyway, yeah, we have that aligned with the field. Okay, so this was the left-hand side. We just say that it's 2 pi x because it's completely aligned. There's no factor. It's not like the magnetic field is going off it. It's completely aligned. And then that's going to be equal to mu naught I. Okay, so we'll say, now we can solve for the magnetic field because we know that there's a certain current. We know what this is. So then we'll say that the magnetic field is equal to mu naught I over 2 pi x. Now this you might have seen before. You should have seen this before. Does anyone know what this law is called? It's telling us that the magnetic field around a conductor carrying a current I, or if there's just somehow a current in one axis, if you go perpendicular away from that axis, the magnetic field strength at that point will be equal to this. Okay. Does anyone know? Does anyone want to be smart and say what law this is? No. Okay. Is this the bio? I don't know if it's probably bio. I don't know. Biot. Savart law. Okay. And if you're to graph that, it will look something like this. We have a conductor, and then we'll have a magnetic field. See, this is going to be like a hyperbola, that as you get close, it'll get stronger, and then it goes like that. It's kind of a hyperbola, 1 over x sort of shape with a factor in front of it. Okay, cool. So that's saying that as you get further away, the magnetic field gets weaker, and it gets weaker at a hyperbolic sort of rate. Okay, so that's interesting. So we know that if there's a current carrying wire, we get a magnetic field, and it gets weaker as we get further away. And it kind of makes sense, because if we have a magnetic field distributed along this sort of circle here, and then it maybe travels over time, even though we're not really considering that, we can see that that has expanded out. Okay, our circle's gotten bigger. The 2 pi x has gotten bigger. Over here, the 2 pi x has gotten bigger, so our magnitude gets smaller, because it kind of this comes from that origin. Okay, so that's our one law that we're dealing. So now we can say, what is the strength of a magnetic field around a conductor? This is all you need to know the magnetic field around a conductor. You can do something in, so just nice to show. And maybe you've seen this. Let's say we have a conductor. Okay, wait, it's not drawn in blue. Is there any question? I'll give you guys some space to ask, so I don't just fly off. Is there anything that I've done so far that you'd like explained a bit better? Basically, we've just seen that the magnetic field around a conductor decreases with respect to like kind of the circle. There's a circulating sort of magnetic field around the conductor. It takes that circular shape. That's also kind of what this law is saying, actually. If you look at like all the calculus and stuff, you'll see that that's what it's saying. That's how we know that it's circles. Well, we also saw it a bit. It's saying that by saying aligning with it. How aligned is it? Then that tells you the current within it. Yeah, and this is actually completely related to a cross product. You can actually replace these two from a integral around the path, a closed path. You can actually make that a cross product, which tells you how much something circulates. Interesting. So that's just a nice introduction for when you guys get that late in your life. Okay, I'm going to continue. Let's say we have a conductor. Okay, and we're going to do the same thing. We're going to say it's carrying a current I, except this time, this is just a nice exercise. Okay, it's carrying a current I, and we're going to say that it has a radius. Let's say it has a radius of b, little b. Okay, and we're going to say that the current is uniformly distributed within it. So this I is the total current in the whole conductor. So we say it's uniformly distributed, so that if we take a section of that wire, so if we just like look at this wire and we say we only want to we take a section of it like this orange section here, we'll know that the current flowing in this is going to be equal to whatever. We'll say that this is a radius. Let's say it's a radius of x. Let's do it in a radius of x. We'll say that it will be x squared. Okay, so it'll be the area x squared times our pi, so pi r squared. Maybe just do it like that. Pi r squared pi r squared, the area of the circle. It'll be so this will be the current in X, will be the total current times by the ratio of the total length. So this will be pi, this will be b squared. Okay, so we'll say that the current within that area is equal to the total current times by the ratio of x squared to b squared, because it's uniformly distributed, so we just divided. So we know that we just divided the fraction of the contained over the total. Okay, wow. Okay, so there, if we look at our law, over here where we had I, if we want to say what is the magnetic field within this wire, okay, we would actually then just change the magnitude of I within it. So we're going to say, well, what is the magnetic field? This did in green, so it stands out over here at this point, okay? And the reason why we're only dealing with one variable, even though this is technically in 3D, is because of the symmetry of the cylinder. So you can just speak about on one axis and everything is symmetrical. So that's also why there's only one variable if you're wondering about this, because this actually isn't 3D. You can't have circulation of things unless it's like there's all the laws and stuff actually have to be in 3D, which is interesting. So we can find the magnetic field at this point inside the wire. So before, where we had this, B of x is equal to mu naught I over 2 pi x, which we derived. You saw how we derived that. We literally just computed the path integral, and then we just literally took it to the other side. Now, if we say that our x is within, we'll say that x is less than b. Okay, so we're inside of this, we're in this range over here. Well, it will just be on one of the sides, whichever side is positive. We're in that range. Now we can say that b of x is equal to mu naught. We'll just leave this 2 pi x here for now. And now I is actually equal to x squared over b squared. So this is actually the current that's contained within it. Okay, so now if you cancel this, x and x, what do we get left? We get mu naught x over 2 pi b squared. Okay, so before, when our law was showing something like this, over here it's showing something like this. It's increasing like a line. If we increase, if this is magnetic field, if we graph it, magnetic field, and this is distance, this is a line. And then this one, before, when the outside was this kind of decreasing parabola. Not parabola, hyperbola. You know the hyperbola, just to remind you guys, this is a hyperbola, 1 over x, like that, which is interesting. It's a very interesting shape, that. So if you were to graph that in total, now you get left with this interesting thing. We have B for the magnetic field strength. Okay, I mustn't, actually the magnitude of the magnetic field strength. Okay, and we'll say at some point we'll label this B at the distance. So this is as we're traveling down x. So we're traveling down x, whatever can be either side. It'll look like this. It's going to go up to B, and then it's going to start doing that parabola thing. And now I think that looks familiar. I think you guys have seen that before, but that is kind of the derivation of that, where you get that flat line, which I think is quite cool. Okay, so now we have the basic understanding of magnetic fields around wires and how we can determine the strength of that magnetic field. The next is going to be it's going to be speaking about that coupling, and we're going to describe that coupling. So to to explain the scenario of what we need to do, I'm going to set the scenario, okay, of like what we want to analyze. And then we're going to start with the thing built, and then we're going to kind of deconstruct it. So kind of the opposite of what we've done, where we built it up. Now we're going to kind of, this is the problem that what you're going to be dealing with. It's like the question, okay? Let's say we have a current carrying wire like this, okay? It's carrying a current, and let's say we put another wire, okay, by this wire, and we want to see the effects. But actually, we're going to, for anything sort of meaningful, with one wire it cancelled couple, but we're going to say that there's a circuit, okay, and you'll see why we need a circuit now. You can have one wire, and then there's all geometries around the magnetic field and how it interacts in the actual wire as one wire, but we're going to say that there's two wires, okay, and we're going to say that this is a circuit, okay, so this is a closed circuit, and at some point, we're going to say they're very long wires as well, but at some point, on each side, this is going to make a circuit. So maybe it's connecting to a load, whatever. I'm just going to draw wires like this to say that they connect. So we know that there's a magnetic field coming from this wire that's carrying a current I. And we know that it's going in circles around it, and it's getting weaker and weaker in a hyperbolic manner. Okay. And we want to know what's the effect. What happens when you have a magnetic field intersecting a loop of wire? What do we get? What law do we have that explains a magnetic field and a loop of wire? Maybe you can say there's a very specific one with a sort of EMF. Okay, so I'll tell you, it's Faraday's law. Okay, which says that we get an EMF produced, okay, when we take the derivative of flux dt. Now remember that flux is this magnetic field times by area. So we take the derivative of that, and then we get it, and then we get an EMF. So if we have a magnetic field, we can also find that there's an EMF between these two wires. And we'll find that by finding the derivative of the flux. But first we need to find the flux. Okay? So this is where we're going to end up. The ultimate goal of this is we want to know what is the EMF produced by this current carrying wire in this circuit. And the reason why we have to have a circuit is because to have a flux, we have to have an area. So this between the two wires becomes our area, like this. And basically we have a flux because remember, this is coming from like that wire there. You see it's intercepting. This we have a magnetic field going through a loop. Okay, it's like the transformer, but now we have it on the side in a way. So yeah, that's kind of where we're going. Is that we're going to see what is the induced EMF on this pair of wire that's making this area that is intercepting a magnetic field. So we have a flux, and we'll have a changing flux even if this current is changing. And then if the current is changing, which will make a changing flux, because this magnetic field will be changing, then we'll get a voltage produced. Okay? It's the same way that if you have a loop of wire and you have a magnet and you move that magnet, you get a voltage. Or if you have a turbine, okay, maybe we have this magnet, let's say, and we somehow move this magnet, maybe we rotate it with steam, we'll change the magnetic field, and if we put coils around that, we'll make electricity. The same reason. It's still okay. Let me just double check that there's no questions. No. Is anyone, are you guys following at all? Have I gone completely, is everyone lost? Or we kind of, does at least one person know what's happening? I just need to make sure. Just one person just say, yes, thank you. Okay, that's all I need. So, the question comes, what is the flux? So let me draw everything again. Bit way more neat this time because we're going to answer that. Because in order to find the EMF between the two wires, we need to know what the flux is. So if we have one, we know how to find the magnetic field, and now we know we have an area between the two wires. So to set the sort of scene, we can say that this is a power line, okay, traveling on in its conductor, and it's producing a magnetic field. And then let's say very close by, there are telephone lines. Okay, now our telephone lines are so this circuit. Okay, and it's underneath this conductor. We want to know what is the effect of that current on these power lines. You'll see that they'll actually affect each other. So let's just label all the variables that are possible. Okay, so we'll need to know the length. Okay, we'll need to know the length because eventually this is going to become an area, and we're going to have magnetic fields intercepting this area. Okay, so we need to know how long it is. We need to know the distance from here to the telephone wires. So let me just label this. So this could be your power line, and these will be your telephone cables. Okay, and then we'll have a distance between those two as well. So that's kind of making the area, because remember this is it's a circuit. It's like a loop. We have a loop of wire and a magnetic field. Okay, so now what is the flux? That's the question. And we'll say that there's just a current I. So I'm doing this all symbolically, and then you guys can apply it in the way that you need. But yeah, I think the symbolic is the best way. And we say, so what is flux? What is the flux? Okay. Well, we know that flux is equal to magnetic field times by area. Okay. So, which is actually, so this, let me draw it. That's actually, you could say, that's if your magnetic field is constant. So if you have an area that's like this size, and we say we have a magnetic field that's intercepting it at right angles, remember, because it has to be perpendicular, then we get that. So you could even say cos theta. So this is maybe what you know, BA cos theta, and then that's if you have if everything's coming at an angle of whatever, like theta. Okay, that will be that angle, because then it's less aligned with the normal of this surface. Okay, so we're just going to say BA if it is aligned. So let's just look at what we're doing. We're looking at the flux in this area. We want the flux. We can say that everything is perpendicular, because if we have a circle, if it's underneath one another, and we have circles coming off this one, we will realize that the circle will intercept like this at a right angle, if you know what I mean. So like if we look at it head on, maybe that's more obvious. If we're drawing circles, so this is our power line that's making these magnetic fields and circles around it. It's not bending, that's a circle. Don't be deceived the fact that it looks like it's somehow being manipulated over there. It's meant to be a circle. So here we can see that these are right angles. Cool, so we don't need to worry about that cos theta sort of stuff. But we do, I should actually not erase that. We can see that also our magnetic field, remember our strength of our magnetic field is defined as B is equal to, what was it? It was 2 pi, it was mu naught I over 2 pi x. That's the strength. So depending what we choose our x to be, so we choose our x, and then that will give us the value of the magnetic field. So if we put whatever, if this is x1, we put in x1 and we'll get the value of magnetic field there. If we put in x2, we'll get the magnetic field value over there. Okay, and it will be smaller as you get further away. So now we're finding the flux of a magnetic field that's decreasing. So in this distance, it's decreasing. Okay. So we can't just times magnetic field times by area. We actually have to do a form of an integral. Okay. We'll do a double integral. So we'll say that it's the integral from 0 to L, and we'll say the integral from A to A plus by B. Okay. So 0 to L, I'll explain that now. And then this is going to be B of x, and then let's say y. Okay, dx, dy. Okay, so we've called this x, we've called this y. Okay, so we say the integral from 0 to L dy, and then we say the integral from a to a plus by b, from a to a plus by b, because this we plus a b there to get there, dx. Okay, so if we do the outer integral first, we can see that nothing's changing. It's symmetrical along this, the y distance over here. So we can actually just compute that. So there's no change in the magnetic field in that direction isn't changing. You know what I mean? So this picture here has one y section. If you continue that y section, it will be the same y section all the way through because it's symmetrical along that axis. So we can actually just say that this is equal to L. So it's just the length, because that there's no like change in the magnetic field doesn't change. So there's no integration actually happening. It's just integrating like a constant. Okay. So then this will become the integral of a plus by b of b of x and y dx. Okay. So now this becomes L, the integral from a to a plus by b of mu naught I, okay, so the current within that, over 2 pi x dx. Okay, so now our flux, now we're integrating our flux, where normally we just times this, we have to integrate it. So if we have our area, we basically, remember integration is just adding. I don't know, maybe that's useful to also for you guys to see briefly. Maybe you didn't know that. But integration is essentially summation. If we have a curve and want to say the integral up to here, we're actually just adding each of the little pieces. And with a finite, we're adding them all together. So this is dx, or whatever, if this is x. And you're adding them all together, and then ultimately you get a sum. If you make that dx go to infinity, you get the area underneath it, but you're adding all these independent little trapeziums. That's one way of looking at it. You know that whole thing. So we're just adding. We're basically looking at this, and we're adding the magnetic field on this one line, because we're just doing the x now. And we're adding what is the strength there, what is the strength there, what is the strength there. That's what this integration is telling us. We're integrating across the magnetic field strength, which is changing. It's a variable. It changes with x. So if we actually do that integration, okay, now what's the integration, the integral of let's take the constants out first. Okay, so mu naught, current isn't changing with x. Okay, and this is 2 pi. Perhaps it could. If it could, then it would be a different scenario. For you guys, it's not going to change. I'm not saying that like, oh, here comes the exam and current's going to change with x. No, it's not. But it could in real life. So then we have a, and then we'll just do the different integration. Doesn't matter. A plus b, and now this becomes 1 over x dx. Okay. Now if we actually do that integral of 1 over x is ln. Okay. So it will become ln x. Okay, so let's just write it here. L mu naught I over 2 pi ln x. So I'm not sure in the Green Book if they go through this derivation or not. They might give you the formula. Maybe they go through the derivation. That the Green Book does actually happen to go through the formula quite a lot. Like I've seen it does do the derivations. Okay, so then there's our limits. If we enter them in, we'll get L is equal, no, not L. This is still B. This is our flux, remember, this is what we're calculating. That's why we're integrating over the two things. And that's how we got this L here. It's because it's one of our triangle that's between the two eyes. This is the one side, and now we're doing the X sort of side. This is XY, this is L is the length. This is just changing. This is the variable. Okay. So then this becomes mu naught I over 2 pi ln a plus by b minus ln of a. Okay. And then because of our lovely log laws having to do with the exponents, when you minus two exponents, it's like dividing. It's like related to that whole exponential world. So now we have L. This is also a function of x, as we'll see now. Flux of x is equal to 2 pi I. This is current. Okay, not imaginary number. There we go. So we arrive from at our flux. Okay, we have our flux. If we want to know the flux between these two wires, okay, let's bring this back up to that, or let's just copy this down here. Let's not even take that. Oh, I took it that side. Well, so now if you see, this will make a lot of sense, all of the variables we have. Okay. So I said, okay, so here we go. We can see here that it's dependent on L. Okay, it makes sense, dependent on L, because it's the length of our flux. Obviously, if we make L longer, our flux will be bigger. So if we increase L, we can see that that would increase. We have ln of A plus by B divided by A. So that comes from these lengths here. Here's A, and then A. So that's the first distance, and then B, and then B. So there we go. So that's our flux, and then those are the variables that would change our actual flux. If we increase B, it would make our flux bigger. But it's weird because we kind of get further away. If we increase A, so if we were to graph this, we'd actually see, which could be quite a fun activity if you go ln, maybe go ln of x plus by y over x. This is random variables, and see the kind of 2D plot you get, and you'll see, like as you change the one and you change the other, what is the magnitude? It'll be like a thing between them. But yeah, so that's how we get our flux. That's the formula for flux derived. Potentially, that's what you could just learn. You could literally just learn this formula if it is this sort of configuration, which I'm pretty sure there's not really more advanced configurations. So, yeah, if there's they're pairs of wires, and then there we go. So yeah, solve for whatever you need to solve in here. This is the equation that we're going to deal with. The final step is that we want to find the EMF. Okay, wait, let's just ask you guys. Anyone else? I mean, like, is there any questions so far? If anyone's following. Any questions? It's probably been a long day. I hope this is not too like that they've lost everyone and they're just sitting here. It's very possible. I did lots of integrals and stuff. Maybe I didn't design this in the most easy to follow way. But yeah, I thought the derivation was nice to see. Anyway, let's continue. EMF, okay, is equal to minus N d flux dt. Okay, N is the number of loops. How many loops are there here? There's one. There's one loop. Can you see it? Like that. These are the closed ends because it's a closed circuit. So there's one. And now we just take the derivative of that flux. So let's say that our current, if we look at our flux at the moment, let's say that this was a function of time, the current. Okay, so then our flux would be a function of x and time and would equal to L mu naught. It's I of t, so c over the 2 pi times by the ln, so that the integral of our 1 over x became a ln, and then here's our geometric sort of spacing, this factor that's going to change the size of it, which takes into account the getting smaller, the magnetic field that's getting smaller. So it starts big and then it gets smaller and smaller and smaller. And it takes into account the distances with that smalling sort of action. If you want to find the flux, this is our only term that is respect to time, because we're going to take the derivative with respect to time over there. So yeah, so if our current waveform, our time waveform will determine our EMF, because if let's say that our current is constant, then if you take the derivative of it, the rate of change with respect to time, there is no rate of change. Thus our EMF is 0. But if this current is like a waveform, let's say maybe it's like a sine wave, okay? Let's say that whatever, let's say that I of t is equal to sine of t, okay? So then we would know that our flux, we'll just say that it is with one magnitude, which we just say A, capital A, that there's a magnitude. Our flux would be equal to mu naught A sine of t over 2 pi ln A plus by B over A. Okay, so those will be the certain things, the parameters of how far away, like the different spacings. And we'd know that E is equal to the derivative, negative derivative of flux dt. So now if we were to actually take that derivative, we'd know that E is equal to the derivative of this flux. So then it would just be everything the same, and then the derivative of sine would be cos. So then it will also put a minus here for the minus. That's very important. And, so that will be mu naught. Sine becomes a cos. If it had a frequency, it would also come out. So if this was like, just say this was like 2 pi wt, then our 2 pi w would come out, because you know the chain rule. And this would be 2 pi, and then this is just a constant, a geometric sort of parameter. And there we go. And that would give us our EMF in volts. It would be the derivative. And there we go. That's pretty much the extent to which this type of question can go. So yeah, that's where we are. We started with a magnetic field being produced around a wire. We then put a loop, an effective loop of wire in that magnetic field, and we got in a flux, and then that flux would produce an EMF. Remember, the flux is an area sort of quantity. It's the area and how aligned it is. There's a nice analogy. It's like if you have a net like this, let's say this is a net, because the flux can be over any surface. It can be some arbitrary surface like this, like a net. Then how aligned it is sort of is the area times by how aligned it is with the net. If there's two current carrying wires, could you use superposition? Yes, you could. That's exactly how you'd do it, is with superposition. Now, I don't actually know, but if we start producing EMFs and now we start producing currents, there's something that's going to be very interesting, is that we're going to have the reverse thing happening. There's going to be this coupling. I think that's what inductance describes, is that coupling, but it's very interesting because the one will produce the other, which will produce the other. So that's actually just like a intriguing sort of thing that I can't actually answer, because I'm sure it will happen, but I wonder how you write that as a formula, because this we're only looking in the one direction. So with that superposition sort of thing, you do the superposition bit. The things that would follow from it actually inducing that, who knows? But yes, that is exactly right. So yeah, there we go. Yes,
Sorry, I have a question. Could you please go to the last equation for the induced EMF? That's possible. Yes. So is W, I'm assuming that's angular frequency, yes?
Yes. That was just everything that was, so it was just whatever was in front of the T.
Oh, okay.
So yeah. So that kind of just came out.
And I'm assuming that us deriving the magnetic flux would not be examinable, right?
So the actual formula, so to derive it, no, I wouldn't say that it's exactly examinable, but I would, like, it depends. Like, so if the configurations change and you understand the derivation, you'll be able to adjust to slight changes, but I don't think there are very many variations, to be honest. So you might be safe not knowing it, but understanding what we were doing definitely will help.
Yes. All right.
Yeah.
Thank you so much.
Yeah. Okay, cool. So there we go. Are there any other questions? Give a few seconds for people to ask questions. Was that fine? I hope. Yeah. Well, okay. I think we can call it. Thank you guys for attending. We had a nice few attending. Good luck. It's crunch time now. Just survive it. Well, you will survive it, trust me. However it goes, if you have to write this up, this is not what I'm saying you must plan for. But let's say that's the worst scenario. Just keep on top, keep positive. It's kind of what will give you your motivation. Don't be defeated. As soon as you think you're defeated, it's over. Just pace yourself. Yeah, you got it. And then your holiday will be so nice. So just keep that in mind. It's worth it. You're working. Life is a bit of work, and you're doing good work, good constructive work. So be proud of yourself. So good luck, everyone. Thank you for attending, and yeah, keep me updated if you guys need anything. Okay, bye. Let me just stop recording.